I would first of all would like to thank the organizers for inviting me to talk and inviting me to see this beautiful institute. I'm really amazed. The talk I'm going to give you, the story I'm going to tell you, is a story of adiabatic pumping that was published in a PRL last year. We did it together with Yuval and Yaroslav Gerasimenko, a student from Ukraine who is now doing his PhD at Leiden in the Netherlands. And yes, I will tell you how it connects to the topics of the conference. Basically, my talk will be structured into three parts. I will give you a brief introduction on adiabatic pumps, and I will emphasize what's important for me. I will formulate the question which I will answer. Then I will tell you how the talk is connected to topological edges. I will tell you about parafermionic zero modes that are implemented at fractional quantum Hall edges. And then I will use parafermions to construct some sort of exotic adiabatic pump. The first two parts are going to be rather pedagogical, not entirely, but close to. So ask questions, you will be able to learn something. And the third part is going to be rather heavy, so ask questions, otherwise you will not learn something. Right. Having said this, let's start. I guess I have to introduce what adiabatic pumps are. And perhaps the oldest adiabatic pump is the Archimedes screw. You rotate it, and at each point in time, the water is in its slowest position, it's in the ground state, but somehow, when you rotate it by one cycle, you transfer water by one step up. This way, you are able to pump water to transfer water from here to there. So these are adiabatic pumps. You do something, your system always stays in the ground state. Nevertheless, you manage to transfer something. That's why it is a pump. And I must tell you that people at Weizmann are fond of adiabatic pumps. This is an exhibit from the Garden of Science at Weizmann. Moreover, the landmark building of Weizmann also reminds you of adiabatic pumps. But I'm comfortable here because an exhibit at the Science Museum of Bangalore also has an adiabatic pump. Right, but all of these are classical adiabatic pumps, and I'm going to talk to you about quantum. Quantum adiabatic pumps are based on adiabatic theorem. Basically, the theorem tells you that you have your system in its ground state, you change some system parameters, and if you do it sufficiently slowly, your system will always stay in its ground state, as long as the system has a gap. And the particular system I'm going to be using a lot in this talk is a two-level system, a very simple system. I have two levels at different energies, separated by energy V, and a particle, an electron or some other particle, can be either at one of the levels or the other level, and there is some tunneling amplitude between the levels. You can see that depending on the V and the eta, the energy spectrum is like this. It always has a gap. And if I start at large negative V, this level has lower energy, my particle sits here. I slowly increase V, I make this level higher, this level goes higher, and the particle will go here if I do it sufficiently slowly. That's what adiabatic theorem states. And let's consider a couple of examples of quantum pumps. Perhaps the most famous one is the Thouless pump. Suppose we have two periodic potentials, one and the other, and we have electrons that live in the sum of these two potentials, so I will combine them the best I can. You can notice that my potentials are not just arbitrary, they have a common period. That's what Thouless did. And he said, let's put some electrons into our system. They have a common period, so our system is still periodic, so we can have Bloch bands. And let's put electrons in a quantity such that we have fully occupied bands and the remaining bands are empty. There are no partially filled bands. All bands are either occupied or empty. That is our system. And then we can do something non-trivial. We can change some parameters of our system so that one of the potentials shifts. And you see, as I shift this potential, I transfer 2 electrons from here to there. That is not very surprising. This one is small. Nevertheless, I transferred 2 electrons, and my system is back to what it was. The potential, the total potential is back to what it was. So I can think this is an adiabatic pump. What Thouless showed is whenever my system satisfies these conditions, the number of electrons I pump, I transfer when I shift one of the potentials by the common period must be integer. So each cycle I transfer one and the same number, say 2 electrons. I do one more cycle, I transfer 2 more electrons. And this is going to be very important for me, because if I transfer 2 electrons each cycle, it means I have some current and I have no noise. I transfer 2 electrons each cycle without any probabilities, deterministically. Another feature that is going to be very important for me is that this is robust against small changes in the potentials, as long as they satisfy these conditions. And why is that? Well, the quantity of pumped electrons has to be integer, and integers cannot change continuously. I can change 2 to 3, but 2.1 is not an integer. Integers can change only in jumps. And that means that if I pump 2 electrons and I change my parameters by a bit, I will still pump 2 electrons. If I change them by a lot, maybe I will start pumping 3 electrons or 1 electron a cycle, but the pump is robust against small perturbations. That's the Thouless pump. Another famous pump is a pump based on quantum dots. We have a reservoir of electrons on the left, a reservoir of electrons on the right, and in between we have a quantum dot, and an electron that comes has some probability of being transmitted, has some probability of being reflected. If we have incoming what? Thouless showed that however many potentials you have, suppose, provided that they have a common period, if you shift one of them or several of them by the common period, you will pump an integer number of electrons. If they are not commensurate, this does not work. I don't exactly know what happens if they are not commensurate. Okay, back to this pump. The properties of electrons being transmitted or reflected are encoded in the scattering matrix. And I can change the scattering matrix by playing with the shape of the quantum dot. So I move one wall or the other, I change the scattering matrix, and I can make a cycle. I move one wall, then the other, then the first one back, then the second one back. It turns out that in this process, you change everything slowly, you pump some charge from left to right. And on average, in one cycle, you will pump this charge, which is expressed like this. What is important for me, I have this integral, and this integral is not quantized. It can be anything. It can be 1, it can be 2, but it can also be 1/2. And if on average I pump half an electron a cycle, I will have noise. Why? Because I cannot transfer half an electron. I either transfer an electron or don't transfer it. So if I, on average, pump half an electron, This means sometimes I do transfer it, sometimes I don't, which will give rise to noise in the pumping current. Let's consider a simple example of such type of a pump. We have left reservoir, right reservoir, quantum dot in between, and some scattering matrix. If I send an electron from left, it has amplitude R of being reflected, amplitude T of being transmitted, and my pumping cycle is going to be like this. I'm going to keep the reflection probability, so the absolute value of the reflection amplitude, constant, and I will change the phase. And when the phase changes by 2 pi, I will call it a pumping cycle because my system comes back to its initial parameters. And you can calculate how much charge you pump. And in fact, these guys calculated what is the probability to pump Q electrons in n pumping cycles. And you see it's a binomial distribution, which tells you that essentially you have probability absolute value R squared to pump an electron in one cycle. Sometimes you pump it with this probability, and sometimes you don't, and that corresponds to this probability. And that gives rise to noise. What is going to be important for me is that this is very sensitive to R. If I'm not exact at what I'm doing, if I slightly shift the wall of the quantum dot, this R is going to change. And with it, the probability, the averaged current, the noise. So I can divide adiabatic pumps into 2 groups, or into 3 groups even, but 2 large groups. One group is the pumps that are noiseless. And this can be robust, insensitive to small perturbations of some class, like the Thouless pump, or these can be fine-tuned. I fine-tuned the reflection amplitude to be 1. I always pump an electron. The second group are the pumps that produce noise. And the only pumps of this type seen so far by the humanity are those sensitive to perturbations. Like we saw, we changed the reflection amplitude slightly, we slightly changed the current, we slightly changed the noise. Yes? No, it's not robust against disorder. It's robust under the assumptions that potential have a common period. That's true, that's not complete robustness. But even so, here, the only parameter I have is essentially the transmission and reflection, and changing this only relevant parameter changes things. While here I have several parameters. To some I am sensitive, to some I'm not. The question I'm going to answer in this talk is, are there any adiabatic pumps that do produce noise, but that are robust, insensitive to at least some class of perturbations? Do such pumps exist? So far, no one has seen any, but I'm going to answer yes, and I'm going to show you one pump of such kind today. That's all I wanted to tell you about adiabatic pumps, and now I'm going to introduce the main instrument which will help me build the pump I want. And this instrument is called Parafermions. We'll approach them step by step. There are many ways to implement Parafermions. There are extremely many proposals, but the conceptually simplest one is based on the fractional quantum Hall. Suppose we take 2 samples of fractional quantum Hall, and I will make a crazy assumption that one of them is formed by spin-up electrons, the other is by spin-down electrons, and they are situated next to each other. You may ask how it is possible. I'll ask you to defer this question till after the talk. But for now, let's just imagine that this is possible. Then there are edge modes. They are actually right-moving spin-up edge mode, I have right moving electrons of spin up, and left moving electrons of spin down. So I have a helical edge, an artificial helical edge. And I ask a question, maybe a stupid one, can I gap this edge out? Turns out I can. If you think I have some excitations going right, some left, how do I gap them out? I allow electrons to tunnel between the two edges, and that should open a gap. There is only one problem. Electrons should flip spin while tunneling. This can be done by spin-orbit coupling, or I prefer to explicitly say I have a ferromagnet on top, and that allows me to rotate my spin of electron while it jumps. So there are ferromagnetically gapped regions. There is another way to gap these edges, and that is by proximity effect of superconductors. We take a conventional S-wave superconductor, and what does it do? It pairs spin-up right-moving electrons to spin-down left-moving electrons. This is exactly what we have here, so it will open a gap. It turns out that these gaps are quite distinct. In fact, they are, people call this topologically distinct. Therefore, between them, there has to be some gapless excitation. These gapless excitations, these yellow stars, are the parafermionic zero modes. Wait for 5 minutes. I do have two, and you'll understand why. I do have two. Yes, same feeling. Say, for simplicity, say it's 1/3. Right, so we want to understand what these parafermions are, what they do, why. For that, we'll need to understand the physics of these domains. The physics of these domains is like this. Let's start with the superconducting domains. Think of a conventional superconductor at zero temperature. It can host a number of Cooper pairs. I can add a Cooper pair, I can remove a Cooper pair. This doesn't cost me any energy. If I want to add an extra electron there, that does cost me energy. That's the conventional superconductor. Those of you who know Majorana fermions, these topological superconducting nanowires, you know that a Majorana nanowire, it can host a number of Cooper pairs, and you can also add one electron into the Majoranas, free of energy cost. If you add the second, they form a Cooper pair, and that's Cooper pairs without an electron, but you can add an extra electron without paying any energy. A very similar thing happens here, but we're fractionalized, so I would call this domain fractional topological superconductor. And on top of some number of Cooper pairs, it can host some fractional charge. I can put an extra quasi-particle, two quasi-particles, three quasi-particles. Say if I put 6 Laughlin quasi-particles, this is like 2 electrons. 2 electrons is a Cooper pair, essentially. So 6 quasi-particles charge 2 is as good as charge 0. That's why modulo 2. I must caution that this is charge. These are not quasi-particles, because the proximitizing S-wave superconductor doesn't really like spin. I won't go into details of how it happens, but the superconducting domain can only host charge, but no spin. The ferromagnetic domains are very similar, except for they can host fractional spin. And fractional spin in a very trivial sense. It's not that I have SO3 rotations, it's I just have SZ projection, and if an electron has spin up here, a Laughlin quasi-particle has 1/3 of a spin up. That's my definition. So I can put an imbalance of 1 quasi-particle here, or 2, or 3, and therefore I have a spin imbalance. This domain has extra spin. As soon as I have spin that corresponds to 2 electrons, you remember, here electrons can jump from one edge to the other. So 1 electron jumps, I had a difference of 2 electron spins, now I have difference of 0. I have 1 up, 1 down, I have no spin imbalance, So again, I measure spin modulo 2 spins of electron. So this system is a topological system. It has topological degeneracy. Its ground state is degenerate, and the degeneracy corresponds to fractional charges or fractional spins inside of these domains. To make things interesting, these charges and spins do not commute. So they are like coordinates and momenta, which means that I cannot know charge and spin of all domains simultaneously. I have to choose the fully commuting set, just like I cannot know momentum at coordinate. I either know coordinate or I know momentum of a quantum particle. Same here. So how can I label the basis of this ground state subspace? I can label it by the charges of the 2 superconducting domains, or just a simple rewriting the total charge into the charge of the first domain, or a less trivial rewriting. I can choose the total charge of these 2 domains and spin of the middle ferromagnetic domain. These are all equally valid bases in the ground state subspace. Now we can, yes? You don't really want to know it. No, it's I times some number, but in fact, because these are not defined as linear, they are defined modulo 2, things get more complicated. Just a number, I times some number. Right, now we're ready to understand Parafermions. The way to understand Parafermions is to try and insert a quasi-particle into this system of domains. As I told you, these domains are gapped, so if I try to take a quasi-particle and bring it here, it will cost me energy. There is a gap here. If I try to bring it here, it will cost me energy again. But I can try to bring it to a domain wall. And what will happen then? My quasi-particle, it has some charge, and it has some spin. I told you that superconductors can host charge but no spin. Ferromagnets can host spin but no charge. So if I bring a quasi-particle here, there will happen a spin-charge separation. Charge goes here, spin goes here. The quantum numbers change. If I take a quasi-particle from the downside, the same thing happens, except for the spin gets decreased, not increased. But otherwise, that's the physics of bringing quasi-particles in. And I can define operators that describe what happens to a state in this ground state subspace when I bring a quasi-particle to a domain wall from either upper or lower quantum Hall sample. And these alpha operators are called Parafermions. You can ask, why are there 2? Exactly because I have spin-up quasi-particles and spin-down quasi-particles. Then, exactly. If I'm going to integer filling factor, I have no quasi-particles, I have electrons. So I bring an electron of spin-up. Because of this ferromagnet, it can immediately jump to electron of spin-down. So there is no difference whether I bring an electron from here or there. That's why there is 1 Majorana per domain wall, but 2 Parafermions. Okay, so we saw that Parafermions essentially appear when you try to insert a quasi-particle into this system, and they inherit many of their properties from quasi-particles. For example, if you want to exchange the order of the 2 Parafermion operators, you will get a plus minus I pi nu phase, which is exactly the statistical phase of Laughlin quasi-particles. If you want to bring many quasi-particles to the same place, you bring, say, 6 of them. This is like 2 electrons. 1 electron jumps here. Then I have one spin up, one spin down electron. They are a Cooper pair, they go here. Which means that if I bring 6 quasi-particles, it's as good as bringing no quasi-particles. So the Parafermion to power 6, or something related to the filling factor, is going to be an identity operator. Finally, these Parafermions, they are useful. If I consider this product of 2 Parafermions, I know about the charge of the superconducting domain. And if I consider a product of these 2 Parafermions, I know the spin of the ferromagnetic domain. Just a brief comparison to Majoranas for those of you who know Majoranas. Majoranas appear in Majorana nanowires, some nanowires with spin-orbit coupling magnetic field proximatized by a superconductor, and they correspond to putting electrons to the wire at an edge, so they inherit their statistical phase from electrons, the anti-commute. You put 2 electrons, this is a Cooper pair, so Majorana squared is equal to 1, as opposed to Parafermion to some power related to 1. The power tells you how many you need to add to get a Cooper pair. Then you can check whether you have this extra electron in the wire or not by looking at the product of 2 Majoranas. Or alternatively, you can look at the product of these 2 Majoranas, which also tells you about occupation of some electron state, which is non-local between the 2 wires. And the analog of that for us is the product of these 2 Parafermions and the spin of the ferromagnet. Okay. Any questions at this point? Good. Because we know everything we need to know about Parafermions. And now we are ready to construct the adiabatic pump. Once more, I'm warning you, it's going to be a bit heavy, so if I'm too fast, stop me, ask me, slow me down. This is the pump in its full glory, but we're going to take it piece by piece. We recognize the 2 quantum Hall samples. We recognize the edges with the domain structure. We recognize the Parafermions. So in fact, we know almost all the ingredients. The new ingredient is the quantum antidot. What is a quantum antidot? It's a depletion in my fractional quantum Hall effect. So I can put a fractional quasi-particle into this depletion. So it's like quantum dot for fractional quasi-particles. Unlike in Mark's talk, just before me, he had quantum dots, and you could put an electron there, or you could maybe redistribute quasi-particles within the dot, but you couldn't put a quasi-particle from outside. That's why I need an antidot. I want to use quasi-particles to tunnel to Parafermions. And yeah, so I have 2 quantum dots. I will allow quasi-particles to tunnel here and there, and here and there. That's a lot to take at the same time, so let's start with something simple. Let's say I have 1 dot and 1 tunneling constant, 1 coupling. So I can put a quasi-particle here, and it can tunnel to a Parafermion. When a quasi-particle is here, the dot is occupied, it has some charge, has 1 quasi-particle, and the superconducting domain has some charge Q1. When it has tunneled, the dot is obviously empty, and the superconducting domain charge got increased by the charge of 1 quasi-particle. And that's a 2-level system, 2 by 2 Hamiltonian. I have some potential of the dot, and I have some tunneling amplitude. That's my favorite 2-level system. So if I start at large negative V, my dot will be occupied. I slowly increase the potential, and the quasi-particle will eventually go to Parafermions. I can allow my quasi-particle to tunnel to a different Parafermion, to this one. Nothing really changes. It's either dot-occupied superconductor in state Q1 or dot-empty superconductor in state Q1 plus one quasi-particle. Exactly same basis, exactly the same 2x2 model, except for if you work out the details, now the tunneling amplitude knows about the charge of this superconducting domain. But you know, who cares about the phase of the tunneling amplitude? So you start again, large negative potential of the dot, you raise it, and you transfer a quasi-particle here. The spin goes to the neighboring ferromagnet, one or the other.
So it's different in the two cases?
It's different in the two cases, and this is exactly represented by this phase difference. Because spin is like momentum for the charge. It's the same two-level system, because I said I can characterize my system by two charges. And the spins, they are like momenta. So if it goes here, it changes the charge. If it goes here, it changes the charge and also a different spin. But you know, the momentum in coordinate representation is a phase. So this multiplies me by a phase. Good. Now things start getting interesting when I allow quasi-particles to tunnel to both Parafermions simultaneously. Then it's again the same two-level system, but now I have interference between two tunneling amplitudes. And once I have interference, I have to worry about it. Basically, I never vary my voltage of the antidot infinitely slowly. I vary it at some finite rate lambda. And what is the probability of not transferring the quasi-particle? The probability of not transferring the quasi-particle is this. If I have some finite amplitude, when lambda goes to 0, I have 0 probability of not transferring it. So I always transfer a quasi-particle from the dot to Parafermions. But if, because of the interference, this amplitude becomes 0 or close to 0, much smaller than my rate lambda, then I don't transfer a quasi-particle. In other words, depending on charge Q1, I can have a gapless system where the adiabatic theorem does not hold. I have 6 possible charges, Q1. I have 6 possible states, and if I choose the phases correctly, for one of them, say 5/3, I will have this gapless system where I never transfer a quasi-particle. So I'm going to define a pump which is not my final pump, but it will be part of it. The elementary pumping cycle is like this. I put a quasi-particle onto the dot, I connect the dot to Parafermions, I sweep the voltage, I disconnect the dot from Parafermions, I sweep the voltage back, the system is back to its original state, it's my cycle. I can repeat it as many times as I wish. So I'm good pumping, but if I fine-tuned this to the point of this gapless system, it's going to be like this. I start at some charge, I pump once, I get to a different charge, I pump twice. Eventually I get to this charge 5/3, and then I never pump anything anymore. We call this topological pumping blockade. Why blockade? Because you start pumping and eventually you stop. 0 current, 0 noise, nothing is happening, blockade. Why topological? Because this Q1 is the topological quantum number of the superconducting domain. It tells you which topological ground state you're in. That's not the pump I promised, but we have to remember that we have a blockade when we pump from QED1. I will fine-tune, and I will never go away from this limit. This is like saying that my potentials in the Thouless pump are commensurate. I can, of course, perturb from there, but suppose I have this. This is not the pump I promised, because zero current, zero noise. I promised you something noisy. So I want to lift the blockade. How can I do it? I can do it by adding the second antidot. Then I put a quasi-particle here. I make it go here by exactly the same way, by changing the potential. It goes here. It changes the charge of the superconducting domain. I can go from here to there. So I do several pumpings from here. Then I reach the blockade, and I do a pumping from here. I lift the blockade. I can pump 5 more times. It is also in my power to not lift the blockade. But I can do it in a non-trivial way. I can say that this is connected here. When a quasi-particle goes here, it changes the charge of this superconducting domain. It doesn't touch this one, so I stay here. I don't lift the blockade in some non-trivial way. As in the previous case, things start getting interesting when I connect it to both Parafermions simultaneously. Because now I have some probability of lifting the blockade and some probability of not lifting the blockade. So I will define my pumping cycle. This is the pump I promised. I won't make it more complicated anymore. I do several pumpings by QED1. I reach the blockade. Then I do a single transfer of quasi-particle from QED2. I don't really know where it goes, but it has a chance of lifting the blockade. I go back. This is a pumping cycle, and it does produce noise, but I promised you universal noise. And this is obviously not universal, because there is some probability of tunneling here and some probability of tunneling here, and depending on small changes to these amplitudes, these probabilities will change. It's not universal, it's not robust, it doesn't tell me about anything good. It's not a Thouless pump. In fact, it is. But for that, we need to look a bit more carefully. The first thing is to realize that we don't just go from here to there or stay, we can actually get to any state. Why? I transfer a quasi-particle from here to there or to there. That's true. So I either go here or stay. But I have a dot connected to 2 Parafermions. For a long time, I'm doing it adiabatically. At some point, my quasi-particle already left. And I have some chance that a quasi-particle from here will tunnel through the dot to this domain and change its charge. Or 2 quasi-particles will go like this, or 3. So I can get actually to any state here. Okay, with some non-universal probabilities based on these tunneling amplitudes. I'm going to argue these probabilities are universal. You have to trust me that just like here, it was good to consider my system in the basis of Q1. Here, to understand what happens here, it's good to consider my system in the basis of S2, of the spin of this middle ferromagnetic domain. So what I need to do is I need to say, okay, I'm in the Q state, I'm expanding it in the eigenstates of spin, I calculate what happens for each spin, then I recollect the states, and I have my probabilities. I don't want to go into details of the calculation. Here is the answer. Here are the probabilities, and you sum over the basis of the spin states. And the important thing is that there are these phases. These phases are the dynamic phases, because when you do this transfer of a quasi-particle from the second dot to Parafermions, depending on the spin, have different energy, so you accumulate different dynamic phase. And in this business of expanding and recollecting, phases are important. So I will have some dynamic phases, and for different spin states, these phases are going to be different. Here are the expressions. Okay, some phases. Okay, some.
You remove the degeneracy.
Yes, when I couple a dot to two parafermions, I partially remove the degeneracy of my system. It was, I had two domains had six-fold degeneracy, so my degeneracy was 36. When I couple the dot, I remove the degeneracy into 6 different subspaces. I reduce the degeneracy from 36 to 6 in the process. That's correct.
Sorry, it wasn't even like, in principle, it was not degenerate, right? Because each of these dots has positive energy or something.
I say a dot is a two-level system. It can be occupied or not, and there is some energy difference between them. Oh, the superconductor. So I imagine that the superconductor, good question, a very good one. The superconductor, I assume it is grounded. And then the charging energy is arbitrarily small. Moreover, this charging energy, it turns out it will know about the total charge if I don't proximatize by two different superconductors. I proximatize by one superconductor with several legs. Then the charging energy will know about the total charge, but not about the individual charges or not about the spin. Right. I don't want to stay here for too long. I want to notice that, okay, here is the dynamical phase, and it depends on the spin state. And most importantly, it has lambda in the denominator. If I do this voltage sweep slowly, my phase diverges, which means that kind of these probabilities are not well defined at all in the limit of adiabatic pumping. And this is something that gives you a hint that something is going on. And let's think about real life. In real life, I do a cycle, I do some cycle, another cycle, another cycle. I don't follow exactly the same procedure. I have small fluctuations. I don't start at voltage minus V node. I start at voltage minus V node plus delta V node. Or maybe the tunneling amplitude is slightly different. Maybe something else. Say, I consider fluctuations of voltage, all other fluctuations go pretty much the same. Then my dynamic phase, the energy fluctuates a bit, the dynamic phase fluctuates, and you see this fluctuation diverges in the adiabatic limit. Which means that my dynamic phase wildly fluctuates, and if I want to consider the realistic pumping, I need to average over these fluctuations. So I take my formula, and it fluctuates independently for different spin states, so this is only non-zero when S2 and S2 prime are the same, then it is 1, you calculate the sum, and you get 1 over d, 1/6 in this case. So you have equal probability of ending up in each of these states after the blockade lifting. And that gives you universal counting statistics. Why? Because my elementary cycle, I do 5 pumpings from dot 1, I pump some amount of quasi-particles, then I do this blockade lifting, and then I pump again. And after the blockade lifting, I can be here, 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 or here, with equal probabilities that depend on nothing but the filling factor, or if you wish, nothing but the topological degeneracy of Parafermions. And therefore, I have probability 1/6 to pump 5 quasi-particles, 1/6 to pump 4 quasi-particles, 1/6 to pump 3 quasi-particles, 1/6 to pump 0 quasi-particles. I have some non-trivial probabilities, I have some noise, and this noise does not depend on how exactly I couple the QAD2. And in particular, you can calculate the average current. It knows about the charge of the tunneling quasi-particle. It knows about the topological degeneracy of Parafermions. It knows about the pumping cycle duration. And if you calculate the noise, you have the Fana factor, and the Fana factor knows about the tunneling quasi-particle charge and about the topological degeneracy of parafermions. That is it. I've constructed my pump with universal noise. So I constructed this pump. Here is the pumping cycle. After lifting the blockade, I have equal probability of going here and thus equal probabilities of pumping 5, 4, 3, 2, 1 or no quasi-particles in the next cycle. And therefore, I get a noiseful pump with universal counting statistics that tells me about the topological properties of my system. Thank you.